Hello. Today we'll have the 10th lecture in our astronomy series. This is chapter 22, neutron stars and black holes, and it will be followed by chapter 24, galaxies. I've skipped chapter 23, however I do strongly recommend that you at least look that over briefly. It talks about the Milky Way. Okay, so you'll recall that a number of weeks ago we talked about white dwarfs and mentioned that they were actually held up more or less by the electron degeneracy pressure. Now we're going to be dealing with objects that are going to have much greater densities, and it's actually going to overwhelm the electron degeneracy pressure. So we saw, for instance, in the last chapter, we learned about type 1 carbon detonation supernovae, which will explode completely and they leave no central remnant. But the type 2 supernovae, which result in an implosion, initial implosion, followed by a bounce, which is the actual explosion, they do leave behind a central remnant, which is much more massive than the remnant of a low-mass star, which of course would result in a white dwarf. Now the densities of type 2 cores will be on the order of 10 to the 17th to 10 to the 18th kilograms per cubic meter, and this is at least 1 billion times greater than that of the density of a white dwarf. So at these pressures, we're actually going to overwhelm the electron degeneracy pressure, and we're now going to be these objects are going to be supported by the neutron degeneracy pressure. So basically, the protons and the electrons now are going to be squeezed into neutrons, and in the process they're going to actually also produce neutrinos. So pressures, at these enormous pressures, for instance, 150 pound, a 70 kilogram person would actually weigh, assuming that they could actually stand on the surface, they would weigh 10 to the 10th tons. Because of the extraordinary gravitational pull. The remnant itself, this neutron star, would be the size of a small asteroid, perhaps 20 kilometers in diameter. And because angular momentum has to be conserved, the original body, the original star, however fast that was spinning, it's now going to be rotating much more rapidly because it's shrunk to this very small size. And so the rotational period of this object will be in fractions of a second. Also, the original magnetic field still remains, but now because it's been compressed to a much smaller volume, the strength of the magnetic field will be amplified by an extraordinary amount, and these fields are going to be trillions of times stronger, for instance, than the Earth's magnetic field. Now, there are objects called pulsars, which are a form of neutron star. It's most probable that all neutron stars are actually pulsars, but what we call pulsars are only those neutron stars that we can view from the Earth that have this property, and it really depends on a matter of perspective. We use something called the lighthouse model to show this. So, you know, on the top of a lighthouse, you've got a light that's going to be rotating around. The light is going to be moving around like this, spinning, and when the light is facing us, we actually can see the beam of light. When it's going over this way, the beam of light is being directed out there. It might be directed out into the plane of the board. Once it's rotated another 90 degrees, then it's going to be directed out here, and finally, when it rotates all the way around again, it's going to be directed towards us. Well, it's that way with pulsars. So a pulsar is a neutron star. Well, what's causing this is there's an accretion disk around the star that is heated up, and this thing is going to be directing beams of some form of electromagnetic radiation perpendicular to this accretion disk. Well, so and it's also spinning, so it's going to really depend on the angle that this presents itself. So you know, if the Earth is over here, we're not going to see this thing. It's a neutron star, but we're not going to see it as a pulsar. But if it's angled so that, for instance, if the Earth were here with respect to that, and it was spinning around like this, we would actually see the beam when it was directed this way. We wouldn't see it until the other side of it got around here, and then we would see we'd actually be able to see it in this. So it's going to have this regular rotation and this regular, rather rapid pulsation that we're going to get. So that's what a pulsar is, and the pulsars could be emitting radio frequency radiation, visible, IR, X-ray. I mean, the whole realm of electromagnetic radiation can be emitted from these objects. Neutron stars, the size of these things, at least have to exceed or meet or exceed the Chandrasekhar limit, which is 1.5 solar masses. So anything smaller than that would not collapse to a neutron star. Would have to be at least within that range. And it's going to run between 1.4 up to the limit, which is about 3 solar masses, and we'll talk momentarily about what happens when it exceeds 3 solar masses. Like I said, we can't directly observe these things, but we can actually determine their mass using their binary companions, because very many of these objects actually have a binary companion associated with them. There's a group of neutron stars that are known as X-ray bursters. X-ray bursters, in the case of an X-ray burster, the companion's mass is actually sucked towards the neutron companion, and it forms this accretion disk, as I've shown here. And the accretion disk is heated up to such a point that it's actually going to be emitting X-rays. So I said you could get all different frequencies of electromagnetic radiation, but in this particular case, these things are heated up to a very great extent. And what will happen, but the neighboring star is actually having its material sucked in here to form this accretion disk. And this occurs about on a time scale that could be measured in an hour or maybe a couple of hours. So it's going to take that long for that much matter to accrete around the neutron star and to heat up to the point where it actually starts to produce X-rays. And then that matter will actually start to be, it's either going to be blown away or fall into onto the surface of the star. And then during that period, you'll have which may again last for perhaps an hour or so, you'll have a period of quiescence where you're no longer going to see these X-ray jets coming out. And then more matter will accrete. And about every hour or so, you're going to have this burst of X-rays followed by, again, this period of quiescence. It's a little bit like a nova that occurs on the surface of a white dwarf, but it's much more powerful than a nova. Now, there is an object known as SS433. It's a neutron star that shoots out more than the equivalent of 1 Earth mass per year of material in the form of 2 jets. So this is actually shooting matter out. And this particular object is known as a microquasar. We're going to talk about full-scale quasars, which it's a similar kind of process, but it's happening on a galactic scale rather than a stellar scale. There are about some 250 or so known what are called millisecond pulsars, spinning several hundred times per second, which is about as fast as a neutron star can spin without actually flying apart. In some cases, the star's equator could be moving at speeds greater than 20% of the speed of light. These are believed to be older pulsars, which if you think about it as the pulsar ages, you'd expect it to actually slow down, but these particular ones seem to have been spun up possibly by withdrawing matter from a companion star. So as the star gets more massive, it actually starts to its rate of rotation actually starts to increase, and as that matter falls onto the pulsar's surface rather than in the accretion disk, it's actually going to cause it to spin up. This occurs in a 2-step process. First, the neutron star forms from a type 2 supernova, and then the second part of that is actually the spin-up process. And it's really kind of the same mechanism as an X-ray burster, X-ray bursters may actually be just a step away from becoming millisecond pulsars. And it's also possible for millisecond pulsars to become X-ray sources as more material continues to accrete from a companion star. So that could go either way. It's kind of an equilibrium type of situation that could be shifted in either direction. Now we get periodic oscillations in some pulsars, and this is indicative of what are known, this can be caused by what are known as pulsar planets, which actually produce a wobble that is detected by Doppler shifts in the emitted radiation. And the planets themselves may have condensed out from the accretion disks of these neutron stars. X-ray bursts also occur at cosmological distances up to about 5 billion parsecs distant from the Earth. Two possible mechanisms are proposed for this. In one, two members of a neutron star binary may actually merge. This is called coalescence, to form a high temperature, they'll merge to form a single object and a high temperature accretion disk. The X-ray burst comes from relativistic outflow of material from the accretion disk. And the second possibility is that a collapsing star begins to form a supernova, but instead it stalls in the middle of the process and forms a black hole instead. And then the accretion disk from the stalled supernova, which is also referred to as a hypernova, restarts the supernova, and this initiates these relativistic outbursts in the two directions as I've shown here. So that, I mean, either of those processes, or maybe both of those processes, may be occurring. So that leads us to what I just mentioned, the concept of the black hole. So when the central core of a star exceeds 3 solar masses as an approximation, so I mentioned that the neutron stars were between 1.4 and 3 solar masses, but when it's greater than 3 solar masses, and this would be the fate of any star that started out at greater than 25 solar masses and started to undergo, became let's say a type 2 supernova. What will be left over at the end of that would be actually a black hole, which is the final stage of stellar evolution of a very, very massive star. So no radiation can escape, and the core of the star actually collapses in on itself to a point. I can only draw it as a circle, but think of it as a sphere. And we can't get any information out of the sphere. So anything that falls in, nothing can leave. That there is a mass that's sufficiently great that the velocity that you would have to go in order to pull away from the gravitational field would actually exceed the speed of light, c, which is 3.00 times 10 to the 8th meters per second. When you get up to this velocity, this is actually the maximum velocity in the universe. It's not possible to exceed the speed of light. So we can conclude then that there might be a mass that's so great that it would be impossible to escape from that mass. And that basically is what a black hole is. We call this distance here, the radius of this sphere. We call this distance here, Schwarzschild radius. Any object that lies within its own Schwarzschild radius is a black hole. So, and we call this boundary here, we call this the event horizon. We actually derive a formula. We have, for instance, this could be a planet, this could be something, a smaller mass that's orbiting that planet. This is the gravitational constant, and this r represents the distance that these two objects are separated. This, of course, is the force. We also know that force times distance, force times r, for instance, is going to be equal to, that will give us energy. If we apply a force over a certain distance, that's going to be the energy. And the energy is going to be equal to 1/2 mv squared. This is the velocity at which this thing that is trying to escape is actually moving. So we can then say that 1/2 mv squared, the energy term here, and the energy term up here would then just be this times r, which would give us, and that's going to be equal to this, would be equal to gm m over r, because that's r squared times r, so that's going to cancel out. That will give us this. And if we make this r equal to the Schwarzschild radius, that's what we're going to call it, we can actually rearrange this equation. So this is going to become mv squared equals 2 gm m over r, and the m's are going to cancel out, and that's going to give us r is equal to 2 gm over v squared. And if we make, as v approaches c, we're going to make v actually equal to c here, then this becomes r sub s. So that is this is actually the formula that we would use, the equation that we would use. We know the value of g. If we know the value, if we know what the mass of an object is, we can calculate what its Schwarzschild radius would be using that equation. That's a handy little thing. So that's how we would define a black hole, an object actually lying within its own Schwarzschild radius. Einstein introduced the concept of special relativity, which is actually useful for explaining some of the things that we've talked about. And in special relativity, there are three principal parts of this. One is that c, which I've already told you, the velocity of electromagnetic radiation, is a maximum speed in the universe. Nothing can exceed that. That's the first part. The second part is that in special relativity, there can be no absolute frame of reference. So we have to talk about things relative to other positions. There's no stationary frame of reference here, or absolute frame of reference. And the third part of this is that space and time are actually codependent. So space and time become a single entity, which we call space-time. So when gravity, if we actually include gravity into the mix that we've got so far, then special relativity becomes what is known as general relativity. And general relativity has a kind of a fourth construct, which is once we include gravity, if we incorporate gravity, then a consequence of that is that space itself, or I should say space-time, has to be curved. So there is a curvature to space-time. One of the things that Einstein predicted using these equations was that light that is coming to us from a distant star ought to actually be curved or actually bent a little bit if the star is just right behind the sun. That is, if the starlight itself is coming from a star that is passing very, very close to the sun. I mean, unfortunately, stars near the sun, you really can't see them, but there is one time when you can, and that's during a total solar eclipse. So some years later, Sir Arthur Eddington, the astronomer, was actually able to measure looking at a particular star that happened to be very, very close to the sun, was actually able to measure that its light had deviated by 1.75 arc seconds. And this is precisely the value that Einstein had indicated that light would deviate from the sun's gravitational pull. So that kind of very strongly supports what was the first positive evidence or test for the theory of relativity. Now, black holes tend to increase in mass over time as material from a neighboring star accretes to their surface. This also increases the radius of the event horizon. Matter falling into the hole is going to be stretched longitudinally. So, a ball falling into the black hole is actually going to stretch out like this, and it's going to be thin laterally and stretch longitudinally. And as it gets down to the point, to the event horizon, it really ought to be at that point infinitely long and infinitesimally thin. So these things are going to be really, there's tremendous tidal forces that occur in matter as it's falling into a black hole. And that these tremendous tidal forces that occur actually cause the matter to heat up to extraordinarily high temperatures, and it will emit X-rays in the process. So although nothing actually gets out of the hull, matter near the hull, that is matter that might be in this accretion disk that's around the hull, is heated up to these very, very high temperatures, and then we're going to get these, again, these jets of energy that are going to be emitted perpendicularly to the accretion disk. So if this is the black hole up here and this is the accretion disk, we're going to have jets of matter going out this way and that way. And anything that is approaching the event horizon is going to be subject to what is known as a gravitational redshift. And this can be explained in this fashion. So as you can see from the equations that I put down here, that photons, anything, whether it's a particle that has mass, I mean, this applies not only to a massive particle, but a particle that absolutely has no mass whatsoever. I mean, we can look at a photon and get a photon's energy using this equation. E equals h f, or h nu, sometimes written as h nu, where Planck's constant times the frequency. So these things still, photons, even though they're massless, still have energy. And as a photon is going to actually have to expend energy in order to pull away from the vicinity of a black hole. It's not yet in the black hole, but once it's in there, it can never get out. But if it's in the vicinity of a black hole, it's still going to have to expend energy, and by doing so, the photon itself will lose energy. So if it's less energetic, that means it's actually been shifted to a longer wavelength and a shorter frequency. That's a consequence of losing energy. So that means it's been redshifted. At the event horizon, the redshift should be infinite. Another thing, as I said, because time is also tied into all of this, is that we're also going to have what is known as time dilation. So as we get closer and closer to the event horizon, time is going to slow down, and apparently will stop once it gets to the event horizon. So, for instance, if you could send some kind of a robot or something into a black hole, and you could actually see it falling into the black hole, and you had your clock and the clock on the robot, you would see that as that clock was approaching the black hole, it would get slower and slower once it actually reached the black hole. Although you wouldn't be able to see it now, it's been so stretched. But what would actually happen is that that time would appear to stop. So we might see, as this thing was falling into the black hole, we might actually see it would never seem to actually fall in. From the perspective of the robot, though, it would be falling in. Would have been torn apart, of course. But you know, if there was some way that we could actually detect this, it would not experience, going in would not experience any change in time. But from our perspective, time would have dilated. The red shift and the clock stopping are both part of the same phenomenon in this case. So according to general relativity, the core remnant of one of these high mass stars will collapse to a point, and this point is called a singularity. And all the laws of physics as we know them really are unable to describe what happens. The laws of physics may actually break down at this point. We don't really know. We need a theory of quantum gravity to actually complete our understanding of what's going on. All we're able to do right now is to estimate the size at which our laws would actually break down. And that size turns out to be much smaller than the size of any elementary particle. I mean, if you put in as the mass of an elementary particle, what you would find is that R, which would be actually that size, would be would be incredibly small. So if we don't know what this is. Is this literally a point which has zero dimension, or is there some actual size to it? But there's no way of us being able to describe that. So how can we observe a black hole, something that where all radiation is rather all matter is actually falling into it, and it itself is not actually emitting any form of electromagnetic radiation? Well, of course, one of the ways that we could do it is by looking at that accretion disk. That's one possibility. The other thing is, what we'd like to be able to do is look at something like stellar transits. So, for instance, as the black hole moved in front of its neighboring star, would that actually cause a diminution in the starlight? Well, that doesn't work because the black hole is very small with respect to the neighboring star. That's one thing, and also because of the great bending of light from the intense gravitational field, that actually causes the whole thing to sort of blur out, so we can't really get a sharp image of that. It's best actually detected by observing the effect that it would actually have on its binary companion. So an example is, for instance, we look at there's an X-ray source that is designated HDE 226868. Star is a blue type supergiant, and it has a binary companion which appears to be a black hole, and this is designated as Cygnus X1. Cygnus X1 appears to have to be 10 solar masses. Its mass is equal to 10 solar masses. It has a surface temperature estimated to be in the millions of kelvins, and it has a small emitting region which is only about 300 kilometers in diameter. These are all, that's 1 light millisecond, and these are all properties that we would expect if that actually were a black hole. Now, centers of galaxies, such as our own Milky Way, have intense radio emissions, also in the form of two of these like 180 degree lobes, and this is believed to be due to supermassive black holes at the center of many galaxies, and these black holes could be anywhere from somewhere in the millions to up to billions of solar masses. And there's also intermediate mass black holes, maybe between 100 and 1,000 solar masses, that seem to form in dense young star clusters. The congested cores of these clusters leads to a runaway growth of extremely massive and unstable stars, which apparently collapse into black holes. And as I said, our own galaxy has black hole. If you did look at the previous chapter, you would see that there's a structure called Sag A star. Stands for it's in the constellation Sagittarius, but this is at the center of our own galaxy, and that is one of these supermassive black holes. One other thing that I have to say about black holes, and then I think I'll conclude with that, is that another way that we might be able to see these things is if we were able to observe gravity, what are known as gravity waves. Just like electromagnetic radiation is propagated in waves, gravity also, the force of gravity also produces waves, but these waves are extraordinarily weak because the gravitational force is a very small force compared to something like the electromagnetic force. It's many orders of magnitude less intense. So while we can detect electromagnetic rays or electromagnetic waves, so far we're unable to detect gravity waves. But if we could see gravity waves from a black hole, if we were able to actually detect it, that would certainly be a very strong indication of the presence of a black hole.